Hi everyone, Mrs. Patel Dane here for topics 9.8, 9.9, and 9.10. So 9.8 is dealing with cell potential under normal conditions. So some of the equations that we might use, you've seen some of these in the past topics. 9.9 talks about non-standard conditions. So say, for example, we change the concentration of something or we add a solid in. What happens after that? And then topic 9.10 talks about electrolysis and something called Faraday's law. So, to go through and remind us, cell potential. Cell potential is the voltage that's going through when we put together, let's say, a voltaic cell, when we have the salt bridge, the electrodes, and the two solutions when we complete the circuit. So, that cell potential is what we call the E cell. So, to remind you, that E cell value is the voltage of the cathode minus that of the anode. So it's a simple little like mathematical thing. You just subtract the two. With this one, we do not switch signs, and this will be a little bit more clear in just a little bit as I go through an example of this. We can also do the E cell value is equal to the reduction reaction minus the E of the oxidation. Oh, sorry, plus. Oh, my bad. Plus the oxidation. And this is if we do switch the signs of E. Ooh. And specifically, we would switch the signs of the oxidation reaction. To remind you that that little like degree symbol, that degree symbol is something called naught. And that's giving us the standard conditions of 1.0 molar, 25 degrees Celsius, and 1 atm if we're dealing with any gases that might be forming. So again, those are standard conditions. Um, to also remind us, a positive E cell is thermodynamically favorable, and that would be like the voltaic or the galvanic cell when we had the salt bridge, right? That was a reaction that was going to occur on its own. A negative E cell value is not thermodynamically favorable. So this would be something if we had the electrolytic cell, and that electrolytic cell had to be powered with a battery in order for it to work. Let's look at some values for delta G or Gibbs free energy. Remember, Gibbs free energy tells us if the reaction is going to occur or not. So if we wanted to compare Gibbs free energy with the E values, we could use this equation right here. And this is something that one of the last few that we are dealing with in our, for the year. So the delta G value is equal to the negative NFE. So we know delta G, that is Gibbs free energy. Gibbs free energy, if it's negative, it's thermodynamically favorable. Whereas if it's positive, it's not thermodynamically favorable. This is also going to be in kilojoules per mole. Then we have N, which is the moles of electrons. So all of this whole thing deals with how electrons are going from one side to the other. And we want to make sure we show that with the moles of electrons. We have F, which is called Faraday's constant. So that is also right in here. Its value is 96,485 coulombs per 1 mole of electron. And coulombs, we can take a look right here, are also equivalent to joules over volts. So this could also be 96485 joules over volts times 1 mole of electrons. And we might need that when it comes to canceling out some units later on. For example, the E value, that one is going to be in volts. So if we had the E value and we have volts here, we can cancel those two out with this. Ideally, I wish they would give you, like, instead of C, they would give you joules over volts. They don't. We'll deal with it. Not a big deal. All right. So those standard conditions. Non-standard conditions. So again, this might be when we are changing the concentration of the solutions, or we're adding a solid to this. A lot of times we'll deal with Q instead of K. So Q was dealing with, again, non-standard conditions. If we have a voltaic cell, and let's say Q is greater than 1, that means that their E cell value has decreased or will decrease. Whereas if Q is less than 1, E cell will increase. So essentially, like, um, we're looking at what's going to happen with Q with respect to K. And I know this part doesn't really make too much sense right now, but hopefully it will in just a little bit. If K is greater than 1, that means that we favor the forward reaction. We're going to produce more of the products at the end. Electrolytic, on the other hand. So remember, electrolytic requires a battery, whereas voltaic is a battery. Electrolytic. There we go. If Q is greater than 1, that means that we increase the magnitude of the E cell. If Q is less than 1, we decrease it. And if K is less than 1, so K is going to be less than 1, it's not favoring the forward. So again, it's going to reverse, it's going to proceed in the reverse direction, and that's not thermodynamically favorable. So hence why we have to have the battery to actually kickstart the reaction. One little thing to note is that solids do not affect the initial voltage. And one of the last little equations that we're going to have, calculating charge flow. And that one is right over here. So it is going to be I is equal to little q over T. So I stands for the current, little q stands for charge in coulombs, which of course we can convert, and the T stands for time in seconds. So again, I is current. That is measured in amps, but amps are also equal to coulombs over seconds. So this one is going to be more user-friendly for what we need it to be. So I would even change that right in here as well. So instead of current, I would make it into coulombs over seconds. And then you can also even change over the coulombs to be joules over volts if you needed to merge that into another equation. The little q is going to be your charge in coulombs. And again, to remind us, coulombs is joules over volts. And T is time in seconds. So this might be something that we are trying to figure out how much time it takes to plate a copper onto a piece of metal, knowing that we have a certain amperage. So that is usually pretty user-friendly, not too bad of an equation. All right, switching up the next one. Sorry, and cool. Sorry about that. All right, now we're good. So for this one, we have a galvanic or a voltaic cell, and we want to make sure that we label everything. So remember, we've got the salt bridge. I tend to use KNO3 in my salt bridge, or at least my examples of this, because both potassium and nitrate are going to be soluble in every substance. So you do not want a salt bridge that's going to form a precipitate with one of the ions in here, because that's not going to make your reaction occur. You need a flow of ions. We also have like a voltmeter or a multimeter that it's connecting to through the wires. We have, let's see, so we're dealing with Cu and Cr, so I'll make this the Cr electrode, I'll make this the Cu electrode. If this is the Cr electrode, I'm going to put Cr plus 3 and Cr plus 2 in here. If this is the Cu electrode, I'm going to put Cu plus 2 in here. Cool. So that is our galvanic / voltaic cell, at least the quick little model of it. The next thing is I need to figure out which one's going to undergo oxidation and which one's going to undergo reduction. So if you recall, all of these E values are given to us for the reduction potential, meaning that each of these are undergoing reduction. The electrons are in the reactants. To know which one is going to be reduction versus which one's truly going to be oxidation, the more positive one we're going to keep as reduction. And we can recall that reduction occurs at the cathode. The more negative one is we're going to flip that equation and make this oxidation, and that occurs at the anode. So automatically I should come to this and be like, okay, let's switch this. Cr plus 2 aqueous produces Cr plus 3 plus 1 electron, and that Cr plus 3 is also aqueous. Because I have switched this equation, I'm going to switch the sign of my E value. So that new E value is positive 0.41 volts instead of negative. B asks us to write the overall equation, so I can take these two half reactions and put them in an equation together. However, I need to look first at my electrons. The Cu plus 2 is gaining 2 electrons. The Cr is plus 3 is going to lose 1 electron. I need my electrons lost to be equal to my electrons gained because these electrons essentially go back up to here. To do that, I need to double this. And to do that, I need to double everything else. So I need to put 2 in front of each of these. But I do not change my value of E. I keep that the same. So now I can look at my reactions and add them together. So I'll add up what's on the left-hand side of Cu plus 2 aqueous plus 2 electrons plus 2 Cr plus 2 aqueous produces Cu solid plus 2 Cu plus 3 aqueous plus 2 electrons. And hopefully these 2 electrons are on opposite sides and the same amount, so I can cancel them. So coming down here for B, I'm taking this, but just getting rid of the electrons. So I have Cu plus 2 aqueous plus 2 Cr plus 2 aqueous produces Cu solid plus 2, that was supposed to be Cr plus 3, my bad. Cr plus 3 aqueous. Cool. So hopefully everything balances out and cancels out as if I need to. So I have the same number of Cus on each side. I have the same number of Crs on each side. And I hope, again, everything gets taken care of in terms of balancing. So over here, I have a total of a plus 6 charge. Over here, I have plus 2 plus 2 times plus 2, so 2 plus 4, which gives me an overall plus 6 charge on this side. So I know that my equation is balanced correctly. For C, I need the cell potential at standard conditions. So that cell potential was right here. I could use either one of these 2 equations to do that. If I switched the sign, I want to make sure I put the correct one, the original one here for the anode. But if I did switch the sign, I could put that new sign here for oxidation. So because I did switch the sign, maybe I'll just throw that one. Again, it doesn't matter which one you use as long as you put it in correctly. So the E value of the reduction and the E value of the oxidation added together, and you're just adding. So 0.34 volts plus 0.41 volts gives us 0.75 volts. And yeah, so that is that value for E. Now I want to figure out my Gibbs free energy from this. So from Gibbs free energy, I can come over here and know that this is the equation that I need. So I need delta G is equal to negative N F E. Recall that N is the number of moles of electrons. So I had 2 moles of electrons here. I'm going to put that right here and continue on that negative. So 2 moles of electrons. I know I need to start canceling out some units, so I'm going to throw this over 1 just to make sure I've got it. Then I have for D, Faraday's constant. For Faraday's constant, I can put in the 96485. And I know I'm dealing with volts over here, so instead of just putting in, oh, sorry, this is my bad, over 1 mole of electrons. I can't forget that. So instead of just putting the coulombs, I'm going to put in joules over volts because I know I need to eventually cancel out volts right over here. So again, this is joules over volts. And to recall, I stole that from right over here. I knew that coulombs was Faraday's constant on the top, but then I switched it so it was joules over volts. All right, cool. I don't know why I extended that line, but that's okay. And then the number of the E cell. So I have 0.75 volts from up here. This needs to be in kilojoules. This is in joules. So put that over 1. Let's make sure that we have 1 kilojoule for every 1,000 joules. And let's cancel units. So we've got moles canceled, joules canceled, volts canceled, and I'm left with kilojoules. And this really would be kilojoules per mole of substance. So we'll kind of play around with that in just a bit. So -2, let's see, times 96485 times 0.75 divided by 1,000 equals -144. If I need to have 2 sig figs from there, I have -140, no decimal point in there. And that's going to be kilojoules. Technically, it's because it's delta G, it's kilojoules per mole. Cool. And then for E, I want to determine the KEQ at 25 degrees Celsius. So from a previous topic, I remember that delta G is equal to -RT ln K. That R is this constant right here. To get out of ln K, I can use my calculator to kind of remind myself if this is the natural log, the opposite, which is right above it, is that E. So, or the little e. Not to be mistaken with the E that we use when we're doing scientific notation. So delta G is equal to -RT ln K. Some people call this RATLink. So then I would know, hey, to divide both sides by -RT and then raise all of that up to the E. So K is equal to E to the negative delta G RT. So we have E is equal to the negative delta G, which we found right here. That's in kilojoules. This is in joules. So I'm going to throw this back into being in joules as well. So I've got 140 and then 123 joules. That's per mole. Then I have my R, and again, that's 8.314 joules per mole time Kelvin. So that's 8.314 joules. And that moles Kelvin should be below this, but instead of having 2 fractions, I'm going to throw that mole and K up there. And then the temperature is at 25 degrees Celsius. So if this isn't on your paper, make sure it is on your paper. This is in Kelvin, so 273 plus 25 gives me 298. Check units, I'm canceling each of those. Perfect, so I want to make sure I have that in there. All right, to put this into our calculator, we've got second E, and then I've got -140, 3 more zeros, divided by, and then in other parentheses, 8.314 times 298. Let's hope this works. Yay. Okay, so I've got 2.8797 times 10 to the -25th. I don't know if I put everything in correctly. Give me 1 second. Oh, no, I didn't. Here's why. This is negative. That's negative, but I need another negative there. So this actually should be positive. So the joy of putting this all in at one time is that I can just second entry and delete. All right, cool. This makes more sense because, and here's why. Here's what I made sense of. This K would have been negative, meaning it would have been going towards the reverse direction. This is a voltaic cell. I know it's a spontaneous reaction. It's going to happen. So it has to have a positive K value. So remember to make sense of your data. So if I'm going to go to 2 sig figs, this is 3.5 times 10 to the 24th. And K does not have an exponent, so I'm going to leave it at that. And I can also say that this favors the forward reaction. Cool. All right, and the next one. If the Cu copper cell was replaced with 4 grams of copper instead of 2 grams of copper, what would happen to the initial voltage? Ooh, this was when I had talked about this. Solids do not affect initial voltage. That was the previous page. So we can say nothing will happen because solids do not affect initial voltage. When they dissolve, they will, but as a solid, it will not. Cool for G. And so this is when we're talking about non-standard conditions right over here. So we're dealing with like Q if we need to or whatever. G, if the Cr cell, the chromium cell, was replaced with 0.10 molar of chromium plus 2 instead of 1.0 molar of chromium plus 2, what would happen to the cell potential? So now we've reduced the concentration of the solution. So we got to think about what might happen. This is conceptual. It is not mathematical. So if we're thinking about this, if we reduce the concentration, the number of products will reduce. So we can say if the concentration decreases, and I'll write it decreases, the products will decrease, meaning that your Q will be less than 1. Remember, Q is like when when something is happening to K. When something happens, it's not at equilibrium yet. We're trying to figure out what's going to happen. So Q is going to be less than K. Sorry, Q is going to be less than 1, excuse me. And we could say that E cell value this one, we would end up, I believe, decreasing this E cell value because it would, um, yeah, because if I'm thinking about like a positive E cell value is going to be thermodynamically favorable, it's still going to be positive, but it'll be less positive. So the E cell will decrease, which I think I changed from over here. So I might need to go back and fact check that for a second. Hopefully I will remind you guys in class if that's accurate or not. Okay, cool. So for H, how many hours will elapse if 1.00 amps were passed through the solution? So now we can play with our little equation over here that we're dealing with time. So we've got amps and have to figure out what our time is going to be. So my time is, actually, let me give you this equation. I is equal to Q over T. I'm solving for T, so I'm going to rearrange this so that T is equal to I over Q. If I know I have, so for my I is my current, that's 1 amp. So 1.00 amps. But I also do recall that for my amps, that's also coulombs over seconds. I want to make it into that instead because I know I have to ask or deal with time eventually in here. Let's see. Oh, JK. Sorry. This isn't right. My bad. This didn't make sense. Okay. So T is equal to Q over I. Whew, that was bad. And again, I made sense of that because the seconds were on the bottom. I'm solving for seconds. That needs to be on the top. So that's what went through my mind as I was going through this. All right, cool. So the Q is going to be the charge in coulombs. So if I think about coulombs, I don't know the charge just yet, but I can solve for that because if I know Faraday's constant and I know the number of electrons, I can get coulombs from that. So I can take the 96485 coulombs for every 1 mole of electrons. I know in this problem I still have 2 moles of electrons. So those moles of electrons cancel. I have Q at the top. And then I want to deal with the amperage that I have. So I have 1.00 amps, but I know that 1.00 amps is equal to coulombs over seconds. Because I don't want to have 2 more fractions in here, I could put seconds here at the top, which is what I want. Cool, and then coulombs cancel. This is in seconds. I want hours, so I'm going to say, make sure I did here, I have 1 minute for every 60 seconds. And I know that I have, I'm sorry, this is looking a little weird. I make these into 2 separate fractions, but I just didn't get the chance to. I know for every 1 hour, I have 60 seconds. All right, cool. So that means that my seconds cancel. Oh, wait, my bad. That's supposed to be minutes. Silly me. That's minutes. So I have hours at the end. Everything else is canceled. That looks like it is good to go. So putting this in, I'll use 2 different parentheses, one for the top, one for the bottom, because I want to make sure that I differentiate between the two. Like, I know I'm multiplying 2 things on the bottom. Yeah, so that is equal to about 53.6 hours. It looks like I have 3 sig figs here, so let's do 53.6 hours. Cool. All right, stretch. We got 1 more to go. And then you're done not only this unit, but all the units, which feels so good. Okay, electrolytic cells. Let's draw a model of this. You have your beaker. You have, let's say, you have a coin, right? So whatever that coin is, you have the electrode. We're running out of space. We have a battery and wires that go connect the two. So here I have Cu plus 2 and 2 electrons producing Cu solid. There's my voltage. And then I have zinc plus 2 electrons producing solid zinc, and that's its voltage. So recall that electrolytic cells are going to be the opposite of my voltaic or galvanic cells. These are not thermodynamically favorable, hence why we have the battery to actually make this happen. So in the voltaic cell, where am I at? My voltaic cell, I took the most negative and made that into oxidation and flipped the equation. I'm going to do the opposite here. So my most positive this time, I'm going to call that one oxidation. I'm going to flip that equation too, and that is at the anode. My most negative is reduction, and that's at the cathode. So I will have a negative E value, and that's normal because this reaction normally would not occur. So Cu plus 2 electrons. This value will now be negative 0.34 volts. Cool. All right, for A, sorry about this. This should be electrolytic. The overall equation, so I'm going to add these 2 together. First, I need to double check. Am I losing electrons and gaining electrons? Yep, I've got electrons on both sides of my reaction. Second thing I want to check is to make sure that I have the same amount of electrons on each side, and it looks like I have the same amount. So essentially what I can do is just cancel those electrons. I'm going just to write it down here for the sake of time. So Cu solid plus Zn plus 2. I know I'm going to cancel out my electrons, so I'm just going to ignore those for right now. Or rather, I've canceled them out, so I don't necessarily need to ignore them. I've already taken care of them. And and Zn solid. So I've taken those two reactions, put them together into one overall reaction. Proceed, determine the cell potential at standard conditions. So again, I can go back to my equation. I did switch signs, so hey, I might as well use this one while I'm here. So my E cell is equal to the E of the reduction plus the E of the oxidation. So this is equal to, let's see, reduction is negative 0.76 volts plus my negative 0.34 volts. So that should be a negative 1.10 volts. And that makes sense because this is not spontaneous. My G value. So my delta G is dealing with thinking about which equation to use, right? So like I know I have voltage. I need to figure out, I know I can have the moles of electrons, and I know what Faraday's constant is. So, and I'm so sorry, you have to squish this in. Delta G is equal to negative NFE. My moles of electrons, let's see, I have 2 moles of electrons. I'll get that over 1 times my Faraday's constant, 96485. I'm going to just switch that to be joules over volts, and that's times moles of electron, because that's just originally part of this constant anyway. And my negative 1.10 volts, get that over 1. Let's see what cancels. Moles cancels, volts cancel, and I'm in joules. So ideally, we would have this in kilojoules. I just didn't ask you. And if they don't ask you, don't do it. So we have negative 2 times 96485 times a negative 1.1, and that is 212267 joules. If we're thinking about, let's see, probably 3 sig figs here, I'm going to go 1, 2, 3. That 2 doesn't do anything to that 2. So this is equal to 212000 joules. To simplify this, I can put this in scientific notation. 2.12 times 10 to the 1, 2, 3, 4, 5, 10 to the 5th joules. So that is my answer for delta G. And then for KEQ. So for KEQ, I know delta G, I know the R, I know T at 25 degrees Celsius, and I'm solving for K. So the K is equal to E to the negative delta G over RT once I've rearranged that equation. This is going to be at 25 degrees Celsius, by the way. So E is, E to the negative 2.12 times 10 to the 5th joules over, and that's, joules per mole. I keep forgetting that. Per mole. And it's moles of the substance, not necessarily moles of electrons. So make sure we keep track of that. The R is from over here, 8.314 joules over moles times Kelvin. So I'll put that mole in Kelvin up there at the top. My T is my temperature in Kelvin, so 298 Kelvin. And let's cross stuff out. So canceling out joules, canceling out moles, canceling out Kelvin. Then you know you've done this correctly. All right, and my handwriting is very messy. My apologies. Looking at the top, I've got negative 2 point. I'm going to put those in another set of parentheses because I like to whenever I have scientific notation, just to make sure everything gets in there correctly. And then 0.314 times 298. And just before I forget, this should be a small value, right? Because K should be very, very much less than 1 because it's not a spontaneous reaction. I'm looking at 3 sig figs, so 6.89 times 10 to the negative 38. And again, no units for that. Cool. For F, if the Cu cell was replaced with 4 grams of Cu instead of 2 grams of Cu, what would happen? We could say that nothing will happen. And then that's because solids do not affect initial voltage. Cool. For G, if we pretty much reduce the concentration of the solution, what would happen? So if we reduce the concentration, so let's say if the concentration decreases, the products will decrease. Meaning Q is less than 1, and your E cell will, let's say, decrease here. I'm trying to remember why exactly, and then over on the previous one, let's say increase for 2G. And I will try to remember to go back through that as well to remind myself. All right, and then H. An electric current of 1 amps is passed through the aqueous solution. How many grams of zinc would be plated in 5 minutes? So this time, they're giving us the time. We have to figure out the mass of zinc. So looking at this, like, I can actually just use dimensional analysis to make this happen. So I'm going to start with 5 minutes over 1. Again, I start with the 5 minutes because I know that that isn't um, a fraction to begin with. So I think I can just start with that. I know my amps, I'm going to need to get that eventually over to seconds. So I'm going to throw this into 60 seconds for every 1 minute. I have 1.00 amps, but that's coulombs over seconds. So I've canceled out seconds, I've canceled out minutes. And then I'm thinking about the number of electrons. I can cancel out the coulombs with knowing that 1 mole of electrons is equal to Faraday's constant, 96485 coulombs. So I've canceled out coulombs. I have a mole of zinc for every 2 moles of electrons. So essentially 2 moles of electrons are being produced for every 1 mole of zinc. And I can easily get us from moles over to grams by using zinc's molar mass. So I have 65.38 grams of zinc for every 1 mole of zinc. Cool. So there's a lot to put in our calculators. I'm going to use some parentheses. The numerator, 5 times 60 times 65.38. Close out that parenthesis, divided by 96485 times 2. Go to syntax error. And, oh, that's fine. Cool. 0.010, sorry, 0.10164, etc. So looking at my units, I think I need probably 3 sig figs. So 0.102, and that's grams of zinc. Cool. That's a lot, right? Like, this may not be intuitive, but hopefully over the course of the entire school year, you can kind of see where I came up with this. This is why when I've been saying and harping on units matter, they really do matter, and they can help you kind of solve through some problems, especially if you get stuck. Have a wonderful, wonderful day. You are done, my dears. This is the end of Unit 9 and the end of the school year. It's been a pleasure. Take care. Bye.